Today we're going to talk about the reaction quotient and Le Chatelier's principle. So a couple of reminders about Q and K. K is your equilibrium constant, and we always write it products over reactants. We use brackets for concentration and parentheses for pressure. So you're looking at the difference between Kc and Kp, concentration versus pressure. You always plug in equilibrium values into your equilibrium expression if you want to find K. But you can use Q if you don't know whether or not it's at equilibrium, or if they tell you it's at like the initial conditions. But Q, you write the same exact expression, still those products over reactants, using brackets for concentration, parentheses for pressure, coefficients become exponents. It's the exact same expression. It's just equilibrium values versus not equilibrium values, or unknown if it's equilibrium values. So then what you can do is you can compare K and Q. All right? So if you calculate Q and you find that it's equal to K, then it's at equilibrium. All right, but if you calculate Q and Q is greater than K, that means we have too many products, okay, because products are on the top. In order to reach equilibrium, we need to make Q smaller to get Q closer to K. So to make Q smaller, we need to make more reactants because that's on the denominator. And in order to make more reactants, we're going to shift the reaction toward the reactant side, or we'll proceed in the reverse direction. So it will, go to the reactant side, just abbreviate. And then, of course, the reverse would be true as well. If you calculate Q and it's smaller than K, if Q is smaller than K, that means you have too many reactants. In order to reach equilibrium, we need to make Q bigger. And to make Q bigger, you will need to form more products. So if Q is smaller than K, then the reaction will proceed in the forward direction and will go to the products. So this becomes very important for a lot of different things. So make sure that you remember if they're equal, it's at equilibrium. If Q is greater, it will shift to the reactants. If Q is smaller, it will go to the products. Okay, so let's look at this problem and see how it applies. We have a fake reaction there, and the Kc value is 3.5 times 10 to the negative fourth. And they give you the initial concentrations are 1 for all of the reactants and products, finding equilibrium concentrations. So we need to go ahead and write the Q expression. Okay, so products C D squared, coefficients become exponents, A, B cubed. And then it says the initial concentrations are 1 for all reactants and products. So we can go ahead and plug in 1 times 1 squared over 1 times 1 cubed, which is nice and easy. It's just 1. All right. So Q is 1 and K is 3.5 times 10 to the negative fourth. And so Q is larger than K. That means Q is too big. I have too many products. I need to make more reactants. I need more reactants to reach equilibrium. So why is that important? So let's go ahead and make an ice chart. A plus 3B yields C plus 2D. We're going to assume that they're all aqueous, right? Because they told us the concentrations are 1 for all of them. Okay, our initial concentrations are 1 molar for all of them. And we need to make more reactants. We found that out by comparing Q and K. So more reactants, that means our reactant side is going to increase, our product side will decrease. And we need to use the coefficients to find out by how much it increases or decreases. So A will increase by X, B will increase by 3X, C will decrease by X, and D will decrease by 2X. All right, so then at equilibrium, we're going to have 1 plus X, 1 plus 3X, 1 minus x, 1 minus 2x, and we can plug that back into our equilibrium expression, which is the same as the expression for q. So we have 1 minus x times 1 minus 2x squared all over 1 plus x times 1 plus 3x cubed. And we know that k is 3.5 times 10 to the negative 4. And so you can solve for x. I recommend using a graphing calculator, and either using the solver function, or you can use the graph function of that to solve for x and find the intersect of the two values. And so when you do solve for x, you get 0.45. And so then when you plug in those, plug in x back into your equilibrium chart so you can find your actual equilibrium concentrations, you get 1.45, 2.35, 0.55, and 0.1. And so those are your equilibrium concentrations, and that would be the answer to this question. Okay, so they give us a reaction with all gases, and they give us the Kp value. It's at 25 degrees Celsius. Remember that K is temperature dependent, so if you change the temperature, K will change. And then they give us a bunch of initial pressures. That's your clue that you can calculate Q using these initial pressures. So let's write the expression. We have the pressure of ICl squared over the pressure of I2 times the pressure of Cl2, and we have 0.1 squared over 0.1 times 0.1, so we just get 1. So if Q is 1 and K is 81.9, K is much larger than Q. In order to reach equilibrium, we need to make Q bigger so that they become equal, and to make Q bigger, I need more products, so it will shift towards the product side. So let's go ahead and make our ice chart now. We have I2 plus Cl2 and the 2 ICl. And we're going to use our pressures here. We have 0.1, 0.1, and 0.1. And we know that it's going to go towards the products, so we will increase the product side and decrease the reactant side. And then we will use the coefficients to find out how much it will increase or decrease. I2 will decrease by x, Cl2 will decrease by x, and ICl will increase by 2x. So at equilibrium, we have 0.1 minus x, 0.1 minus x, and 0.1 plus 2x. From there, we can plug this into our equilibrium expression. So we have our value of K is 81.9. And it's the same expression as Q, because we still put products over reactants. But let's go ahead and plug in the equilibrium values. We have 0.1 plus 2x squared, 0.1 minus x, 0.1 minus x, and then you can solve using your graphing calculator, and you get that x is equal to 0.073. So then if we take that value of x and plug that back into our ice chart, we get that the equilibrium value pressure for I2 is 0.247 for I2, 0.027, 0.027 for Cl2, and then for the ICl you get 0.246. And that's all in ATM. And those are our equilibrium partial pressures. Okay, last example, we have this fake reaction, and they give us Kc is 128. The initial values are in the table, and then they give us, they want us to calculate the value for Q to determine the direction that the reaction will go. So we want to write our Q expression, products over reactants. So we have our B squared times C all over A, and then we can plug in those initial values. B is 3.2 squared, and C is 1.85, A is 2.50. So then go ahead and calculate Q is equal to 7.58, and that is smaller than K, which is 128. So Q is too small. Well, in order to reach equilibrium, we need to make it bigger, and the way that we do that is by creating more products. So the product side will increase and the reactant side will decrease. Use the coefficients. It will decrease by x, increase by 2x, increase by x. And then when we plug in those values, 2.5 minus x, 3.2 plus 2x, and 1.85 plus x. Let's go ahead and plug in that into our equilibrium expression. So 128 is equal to products 3.2 plus 2x squared times 1.85 plus x all over 2.5 minus x. And when you solve for x, you get that x is equal to 1.48. And then we need to plug in the value of x back into our ice chart to find the equilibrium concentrations. So for A, we get 1.02 molar. For B, we get 6.16 molar. And for C, we get 3.33 molar.